Hello, everybody. This is Mrs. Masteller, and we are starting Chapter 7 today. So our first section, as you see, it says 7-1. It's titled, we're doing exponential functions, so focusing on growth and decay. All right, so starting with the basics, how do we graph an exponential? So an exponential function is of the form y equals a times b to the x. And then a few details about it. It says that a cannot be 0. So that's the first thing. So a cannot be 0 because, well, that would just basically not make it an exponential anymore. You would just have the equation y equals 0, which would just be a horizontal line going through y at 0. Okay, now moving on to b, so some stipulations about b. b has to be a positive value, so b has to be greater than 0, but it's not going to be 1. So b could be any positive number, just not 1. Only because if b were to be 1, it would honestly just make the problem way too easy. Because if you had 1 as your b, and then you're raising 1 to basically any power, well, 1 to any power is just going to be 1 anyways. So again, those are just the stipulations when it comes to an exponential. All right. So it says we're going to graph y equals 2 to the x power. This is our exponential function. And they have a table set up for you. So they already have numbers plugged into for x. So we got -3 through +3. So all you have to do is take those x's, plug them into the function, solving for the y. So for instance, when you plug in -3 for x, for the first one, you're going to have that y is equal to 2 to the -3rd power. So now it's just about calculating. What is 2 to the -3rd? Well, that's just going to be 1/8. And then plugging in -2 for x, so y is going to equal to the -2. So what's 2 to the -2? That's 1/4. Plugging in -1 for x, so y is going to be 2 to the -1, and that would just be 1/2. And then plugging in 0 for x, y is 2 to the 0 power, 2 to the 0, anything to the 0 is just 1. Plugging in 1 for x, which should be a little bit easier now, 2 to the first power is just 2. Y equals 2 squared, so 2 squared is just 4. And then y equals 2 cubed, so 2 cubed, that's going to be 8. Okay, so graphing this out, let's see what an exponential function looks like now. So I'm going to go back 3 and then up just 1/8. So that's going to be about right there, just a smidge above 0. Then going back 2, going up 1/4, just a little bit higher than the last point, just a little bit. And then going back 1, going up 1/2 now. Now we're in the middle. Okay, 0, 1, that's our y-intercept. So that's where it's crossing over the y. And then going to the right 1, up 2. Going to the right 2, going up 4. And then going to the right 3, up 4, 5, 6, 7, 8. All right, connecting your points. And you can see what an exponential function looks like. Okay, so there's some characteristics about this function that we want to talk about next, but you can obviously see how rapidly these functions increase. And to me, that's what I think about. When I think of something being exponential, I think of something growing at a very rapid pace. Okay, that's exactly what your graph should look like every single time. But it is going to extend again in both directions because there's more to it than just these points. These are just the points that we use to graph our function. But there's a lot more x's, there's a lot more y's involved. Okay, so just make sure you put the arrows on both ends, but it also just kind of levels off just above the x-axis. So on the left-hand side, when it's going all the way over to the left-hand side, it's never going to actually be on the x-axis, nor is it going to dip below. So it's never going to actually be in the negatives. Okay, in this case scenario at least. So characteristics I want to talk about. So filling these bullet points, it says the domain is going to be the set of, it's always going to be all real numbers. Because you could plug in anything you want to for x. So your domain again is referring to the x values. And again, you could plug in anything you want to for x. We just chose to plug in these numbers, but you could plug in a lot more numbers if you want to. You could plug in fractions, decimals, whatever you want, whatever your heart desires. Okay? Our next bullet point now says the blank is going to be in blank of the graph. And that's kind of something I was already talking about. The x-axis is acting as an asymptote, which we know what those are because we did those back in chapter 8. So what an asymptote is, again, if you want to make a little reminder to yourself, it's kind of like a boundary. Think about it like that. It's a boundary that you can't cross, you can't touch. So again, our points, our graph itself, it just kind of levels off just above the x-axis in this case. But again, it's never going to cross it or touch it. So the x-axis is going to be our asymptote. Okay, the range now, so we talked about the domain already. The range is going to be the set of all positive values. It's going to be all positive numbers as long as a is positive. And it's going to be all the negative numbers. It's going to be a bunch of negative values if A is a negative number. So it all depends on what your A value is. So let me go back up here and point it out with this graph. So we graphed again y equals 2 to the x. 2 is technically our B value. So again, if you compare it, B is going to be whatever's being raised to the exponent. So what is our A value? Technically, this is just y equals 1 times 2 to the x. So our A value is positive 1. So as you see, since our A value is positive 1, look at your range now. Look at your y coordinates. All of your y's are positive, right? Why? Well, because your A is positive. So if A is positive, the range will all be positive. If A is negative, the range will all be negative. Okay, the next one says the graphs of y equals a times b to the x and y equals a times 1 over b to the x. These are going to be reflections. They'll be reflections of each other across the y-axis. Okay, so let me kind of highlight what this means. So we graphed y equals 2 to the x, right? If we were to graph y equals 1/2 to the x, okay, which is basically the reciprocal, right? So 2, the reciprocal of that would be 1/2. If we were to graph this out, so here's my x-axis, my y-axis, we would see the same function as we just graphed, but just flipped over the y-axis. So basically, you would see it starting up here in quadrant 2 and just sloping down and then just decreasing, getting closer and closer to the y. So if you just take this image on the left-hand side again, just flip it over the y-axis, it's going to be symmetric, reflected over the y-axis. Okay? The last one says the graph contains the point, it always contains this point, 0a, which means the y-intercept is going to be whatever your a value is. So where it crosses over the y-axis is your a value. So if I go back up here and refer to this one, my a value, like I said, is positive 1. Guess where it's crossing over the y-axis? At positive 1. Okay, so a lot of little details, a lot of cool stuff happening with exponential functions. But the next thing we have to talk about is what's the difference between exponential growth and decay. Okay, it all depends on what the base is. Whatever your b value is, whatever the base of the exponential, so whatever the value that's being raised to the exponent, whatever that number is, that's going to determine if it's going to be exponential growth or decay. So it says it's going to be growth as long as b is greater than 1. So that's the key thing. Let me give you an example first, and then I'll come back to the description. So as an example, if you have something like y equals 2 times 3 to the x. So if this number is bigger than 1, it's going to be exponential growth. And what you're going to actually see in the function is as your x's increase, the function also increases. So if it's going to be exponential growth, as your x's increase, the function itself increases too, which is exactly what happened in our first example. Okay, the bigger the x's were that I plugged in, as I went down through the table, you could see how the y's are increasing. You could even see that graphically too, right? So if I kind of keep increasing along my x-axis here, my function is going up, it's increasing, okay? And then for exponential decay, now, if your b value, it says, is in between 0 and 1, so we're talking about fractions, decimals, like 0.01 or 1/2 or 2/3. Okay, those are all numbers between 0 and 1. So let me give you an example down here. If it was like y equals 2 times 1/3 to the x, so again, if this number is in between 0 and 1, then it's going to be exponential decay. And what you're going to see for this one is as your x's increase, the function is actually going to decrease. Okay, it's going to be decreasing from left to right. Your y's will be going down. So that's kind of similar to the second graph I did up here. Okay, we obviously don't have a table to look at, but you can actually see as the x's were increasing from left to right, the function's actually going downwards, right? So as my x's increase from left to right, function's going down. It's exactly what you see in the graph. Okay, so we have to be able to identify, is a function going to be exponential growth or decay just by looking at that b value. So if you identify, for example number 1, our b value is 0.5, so that's between 0 and 1, this would definitely be exponential decay. For number 2, our b value is positive 5, which is bigger than 1, so that'd be exponential growth. Example number 3, well, first of all, we have a negative exponent, so we can't really properly identify it if we have a negative exponent. So make it positive. What you're going to do, just flip it around, reciprocal. That makes it a positive exponent. Now properly identify. So looking at my b value, it's 3/4. That's between 0 and 1, so this would be decay. All right, that's all you got to do. So moving on to the next page, similar idea over here. The directions do say to tell whether each one is exponential growth or decay, then actually graph it out. So for number 4, is this going to be growth or decay? Look at my b value. That's going to be growth. And then for number 5, my b value is 0.5. This is going to be decay. All right. So now we want to just simply plug numbers in for x and then solve for the y. So plugging in numbers for x, you always kind of want some negatives, some positives. So I'm just going to kind of stay in this range. Just kind of some easy numbers to plug in. I'll do the same over here. Just plugging in these numbers for x, solving for the y. Okay? So when you plug in -2 for x, just be careful. So make sure you're doing proper order of operations. That's all. So when I plug in -2 for x, first thing you should actually be doing is the exponent. So you want to raise 3 to the -2. Figure out what that is first, and then times that by 1/2. So if you don't know what that is, you can always pull up your calculator. Okay, go through the calculations, but we should be able to do this in our head. Negative exponents. 3 to the -2, that's 1/9. And 1/9 times 1/2 would just be 1/18. Now plugging in -1. So if I plug in -1 for x, you can erase this one. Plug in the next one, -1. So 3 to the -1, that's 1/3. Timesing that by 1/2 would be 1/6. Now plug in 0 for x. So 3 to the 0 power, that's 1. And then 1 times 1/2 is 1/2. Plug in 1 for x, so that'd be 3. 3 to the first power is just 3. 3 times 1/2 is 3/2, but that would be 1 1/2. Plug in 2, 3 squared is 9. 9 times 1/2 is 9/2, but that's 4 1/2. Okay, so let's graph this out. Again, this is going to be exponential growth. So as we graph this, so I'm going to go up 1/18. Go back 1, go up 1/6. 0 1/2. So again, that's the y-intercept based on our a value. Whatever your a value is, that is your y-intercept. So it's crossing over the y-axis at 1/2, and then going over 1, going up 1.5, going over 2, going up 1, 2, 3, 4.5. And now I'll just connect my points, and there's my function. Okay? Domain again is going to be all real numbers. So I'm just going to put negative infinity to positive infinity, interval notation. As far as my range goes for this one, again, you really only have 2 options. It's either going to be strictly positive values for the range or strictly negative. So, and it's all based on your a value. Since my a value is positive, all my y's, as you see in the table, came out positive. So again, it's never going to go below the x-axis. So as far as my range goes, I'm just going to say it's from 0 to infinity with parentheses around them both. Okay, because it's never going to actually be 0 itself. That's why it's not going to have a bracket. It's just going to be from 0 to infinity, but with parentheses. Okay, so we're not including 0. So for the next one, plugging in our numbers for x, and then solving for the y. So when I plug in -2 for x, if I do 0.5 raised to the -2, let's see, let me just do this one real quick. So 0.5 to the -2 power, that should be, so what's 1/2? Raising it to the -2, so that'd be 4. 4 times -2 should be -8. And then plugging in -1 for x, so y equals -2, 0.5 is now to the -1, so that's 2. 2 times -2 is -4. Plugging in 0 for x, so that's going to be 1. 1 times -2 is -2. Plugging in 1 for x, so that'd be 1/2 times -2 is -1. Plugging in 2 for x, so that would be... So that'd be 1/4 times -2 would be -2/4, so that's -1/2. Okay, so we got our table. Now plotting our points. So going back 2 and then going down 1, 2, 3, 4, 5, 6, 7, 8. I think that's 8, right? 1, 2, 3, 4, 5, 6, 7. Yep, that's 8. Going back 1, down 1, 2, 3, 4. 0, -2. So again, because my a is -2, that's where it's crossing over the y. And then 1, -1, 2, -1/2. So just below the x-axis this time. Okay, so our domain again does not change. It's all reals. Could plug in anything we want to for x, all real numbers. The range, though, this time, since it's underneath the x-axis and all my y's are negative, it'd be from negative infinity up to 0 would be my range. Okay? So now the last thing we have to do is we're going to talk about this growth and decay model. So it says we're basically going to be using this model to simulate some growth and decay situations. So the final amount, just knowing this formula, the final amount, that's obviously what we're solving for, A of t. The initial amount goes out front, so whatever you're starting with, and then you see the 1 plus or minus r inside parentheses. That's going to be your rate of increase. R is going to be your rate of increase or decrease, I should kind of say. But you're just going to be doing one or the other. So depending if it's growing or if it's decaying, then you want to do 1 plus r for growth and 1 minus r for decaying. And then t is just simply going to be the time. So whatever the time period is that we're talking about, just plug in the time. Okay, so let me kind of show you how this is done. So it says a GPS system uses satellite information to locate ground position. A booth surveying firm bought a GPS system for $12,500. So that's the initial amount. That's A. So again, just using this formula, 12,500, that's the lowercase a. We're going to plug that in for A. The GPS is depreciating at a fixed rate, so that's our rate is 15%, so that's R. But you never want to use percentages. Just convert that to a decimal. That's 0.15. And we're trying to find to the nearest dollar, what's the value of the GPS going to be in 7 years? And that's our time, 7 years. Okay? So we have everything we need. We just need to figure out, again, we bought this GPS system. Pretend like you're a boo, and you bought this GPS system for $12,500, and it's going down in value every year by 15%. So what's it going to be worth now in 7 years? So when you plug this all in, you're doing 12,500, and then it's going to be 1 minus, because it's going down 15%, and then raise the 7th power. So just going through and calculating, just remember order of operations. So your PEMDAS, please excuse my dear Aunt Sally, you want to do the parentheses first, so just subtracting. So when you subtract, that's going to be 0.85. Next thing you'd want to do is the exponent. That comes next. Figure out the exponent. And then the last thing is just simply multiply it by 12,500. But it does say to the nearest dollar, you want to actually round your answer here a little bit. So to the nearest whole dollar, what you should come out with, if you do this calculation, it comes out to be $4,007. So you bought the GPS system for $12,500, but only 7 years later, now it's only worth $4,007. Okay, for the last one, number 7, Claire is investing $5,000 in an account. It's paying her 3.25% interest every year. So how much will her investment be worth in 10 years? So again, her initial amount, what she's starting with, is $5,000. It's going up 3.25%. But again, as a decimal, it's 0.0325. And then time would be 10 years. So plugging this all in where it goes. So she's starting with 5,000. That's the initial. She's earning this rate, and then time would be 10 years. So plugging this all in, again, starting with my parentheses. That's just 1.0325. Next thing again, exponent, figure out what that is to the exponent, times it by 5,000. But $5,000, if she just let it sit there and accumulate interest, it would now turn into $6,884.47. And there you go. All right, there's our first lesson. So let us know if you have any questions, and that is it for today.